Hi everyone. My name is Brian Moser. I'm a PhD student from the German Research Center for Artificial Intelligence, and I'm very glad to have the opportunity to share our work with you. The presented work is Waving Goodbye to Low-Res, a diffusion-wavelet approach for image super-resolution. As the name suggests, we present you a diffusion model that can operate in the frequency domain to enhance the performance of image super-resolution. The presentation is structured as follows. First, I will introduce the motivation behind this work. Next, I will present the necessary background information necessary in order to understand our method. Then I will present our method, DiWa, which is the short name version of diffusion wavelet. We will then evaluate DiWa with experiments. And last but not least, we will draw conclusions from this work. Without further ado, let's dive into the motivation. So, what is image super resolution? In simple words, the task is about generating high resolution images from low resolution ones. So, to be precise, there are actually two categories. One is single image super resolution, with the goal of super resolving one low resolution image to one high resolution image. And then there is multi-image super resolution, with the goal of super resolving one or many high resolution images from many low resolution images. And the presented work here focuses on single image super resolution. Image super resolution has a wide range of applications. Some of them are listed here. Of course, the classical application is to enhance everyday images, but then there's also surveillance and security applications, especially interesting for urban security. Image super resolution is also interesting for remote sensing, so enhancing satellite imagery for Earth sciences. And then image super resolution can also be very critical, for example, in medical imaging. Where are we today? Well, traditional regression techniques such as standard CNNs, as you probably know, already produce nice results for at least lower magnification ratios, and which is usually employing a scale of 4 and lower. However, they struggle to produce good results for higher magnification ratios. And this is because higher magnification ratios require super resolution models that are capable of hallucinating information beyond interpolation. And this typically falls under the umbrella term of generative models. And recently, a category of generative models called diffusion models was introduced that challenged the long-standing dominance of GANs and others. And this is something you probably know, and as you also probably know, they are very well known from applications like Midjourney, Stable Diffusion, or DALL-E, and they can produce high-quality images that resemble real data. So, what is actually the challenge of diffusion-based super-resolution models? Well, the main obstacle is that this problem is inherently ill-posed, as shown in this example. Many high-resolution images can be valid for any given low-resolution image, and this can become even more pronounced for higher magnification ratios. The quality or the realism of super-resolved images is primarily driven by their high frequency information. So human observers would also say they describe details. In simple words, high frequency describes high pixel variations, or to put it differently, pixels that are abruptly different from their neighbors. And the question that naturally arises is, wouldn't it be more beneficial to apply generative models in the frequency domain if frequency is the most important thing of a super resolved image? And the answer is yes, and it is, and we will see how. But let us first discuss some background information. The first thing we need to understand is how to translate images from pixel to frequency space. And for that, we can use a common transformation called Discrete Wavelet Transform, which was already applied for regression-based methods and is also used in applications like image compression. The Discrete Wavelet Transform decomposes an image into 4 frequency subbands, as shown here in the figure. The interesting ones are denoted by HL, LH, and HH, as they describe high frequency information in the horizontal, vertical, and diagonal directions. One benefit of discrete wavelet transform is that it reduces the spatial area of images by a factor of 4, which we will exploit in our method for fast inference. The next thing we need to discuss is diffusion models itself. So I will keep this short as they become like the generative models in various applications. So given a low resolution image, we will degrade it with Gaussian noise in the forward diffusion process in many time steps. And during the backward diffusion, we will revert the process using a parameterized model, usually a standard CNN, and condition it with the low resolution image and the current time step. In each time step, we predict the noise added during the forward process and will remove it. And in the end, this will form a clear transition from noise to real images. So in total, we will generate a high resolution image via iterative refinement. And so what happens if we combine those two things? Well, then you get DiWa, a diffusion-wavelet approach for image super resolution. What you can see here is the overview of our method and its loss function above. And for now, you can actually just ignore the overview. As mentioned before, DiWa uses the frequency domain, which you can see in the loss function. So it uses the discrete wavelet transform to transform images to the frequency domain, denoted by the inverse hat symbol here. Moreover, DiWa uses an initial predictor, here denoted with a G. And later in the ablation study, we will show that both components, the discrete wavelet transform and the initial predictor, are essential for balancing good performance and fast inference. The initial predictor consists of a simple concatenation of 10 convolution layers and is inspired by DWSR from Guo et al. And as you can see below in the overview, we first upsample the image to the desired target size by using bicubic interpolation. And then we translate the image into the frequency domain by applying the discrete wavelet transform. And next we apply the initial predictor. And the initial predictor is essentially inspired by regression-based techniques and gives a good initial super resolution prediction. And in a parallel branch, we use the decomposed low resolution image to guide a diffusion model, which then predicts details that the regression-based technique is unable to. And ultimately, we combine all branches and apply the inverse of the discrete wavelet transform to get the final super resolution prediction. So let's see how this method performs in practice. First of all, we use the lightweight version of SR3 as the backbone for our diffusion model, and we test DiWa on 2 tracks. So the first one is phase super resolution and the second one is general super resolution. For phase super resolution, we compare DiWa with SR3 and follow the training and testing procedure presented by SR3. So train on FFHQ for 1 million training iterations and evaluate on syllable HQ. For general super resolution, we compare DiWa with SRDiff and follow the procedure presented by SRDiff, so train on diff2k, and for 100,000 iterations, and which is significantly lower than SRDiff, as we found out that DiWa was converging much faster for the general super resolution case. And we will compare DiWa against SRDiff on the diff2k validation set, and we will also compare DiWa against other state-of-the-art generative models on the test datasets Z5, Z14, BSDS 100, and General 100. It's important to note that DiWa uses much fewer parameters, so in total 92 million in comparison to SR3 with 550 million parameters. And we can see a similar pattern when we optimize DiWa for general super resolution, which resulted in 9.3 million parameters instead of 12 million. We achieved this by using smaller channel sizes, which was sufficient enough as the images in the frequency domain compressed the spatial information to the channel dimension. For phase super resolution, DiWa clearly performs better than SR3, in regression-based metrics like PSNR and SSIM. And we also see clear improvement for the perception metric LPIPS, where lower denotes better. Below you can see a visual comparison between the outputs of DiWa and SR3. And an interesting behavior of DiWa is its focus on the high frequency details, which you can also observe here in the skin regions and especially in the hair region. DiWa produces more high frequency details than present in the actual ground truth image, which is very interesting. And this is also observable in the Fourier magnitude spectra. For that, we first transformed the image to an YCB-CR color representation and transformed the Y channel, which represents the structural information, via a fast Fourier transform. Then we calculate the L1 error to the corresponding high resolution image. Therefore, the brighter the color, the higher the error. And also, the nearer a pixel location is to the center of the image, the more it represents low frequency error, and vice versa for high resolution. As we can see, SR3 not only exhibits overall a higher error, but also especially in the high frequency area, in which you can see in the outer rings of the spectra. For general super resolution against SRDiff, a similar pattern emerges when evaluating on the diff2k validation set with 4 times upscaling. And we outperform SRDiff in PSNR by 0.68 decibels and LPIPS by 0.032, and are on par regarding SSIM with a difference of just 0.01, which is marked by the red box here. And again, when we look at the visual comparison, we can see that DiWa produces much more high frequency details than SRDiff. Here we zoomed in 2 times in the eye region, and we can see much higher and finer details around the pupils and also in the texture around the eyes. A similar pattern emerges compared to other state-of-the-art generative models besides diffusion models. So again, we measured the perception metric LPIPS here, where lower signifies better image quality, and as a result, we also outperform on all test data sets except for set 5, which is not that tremendous because set 5 only consists of 5 test images. Finally, let's take a quick look at the ablation study. As you can see, both the initial predictor and the discrete wavelet transform improve the performance of SR3 significantly. However, we can see that the discrete wavelet transform performs the best in terms of throughput, so images per second, and VRAM consumption. And by combining both the initial predictor and the discrete wavelet transform, we get the best balance between image quality produced, and which you can actually also see by the best PSNR value here, and between the computational demands expressed by throughput and memory consumption. So it literally hits the sweet spot. So what are the conclusions of this work? Well, we presented DiWa, a diffusion wavelet approach for image super resolution, and it enables diffusion in the frequency domain and it exploits an initial predictor for the best trade-off between image quality and inference time and less memory consumption. It achieves better image quality due to high frequency detail enhancement in the frequency domain and reaches overall, with all compared methods, the fastest inference by roughly 250% while using way less memory. So I want to thank you for listening, and if you have any remaining questions, you can reach out to me via my email address shown here. Thank you very much.